up for the background in MEG, so I will do it.
Both Yehuda and Ori are they think that they present today something.
Yes.
So
that's fine. Yeah, here. I don't know if you can see it. Yeah. You can see this? Light is closed already. Yeah, so you should all tasks, and so nobody signed up for the MEG, so I will say something about it, and or I put you here. So if you didn't see it, then we need to maybe you can prepare it until Sunday.
Sunday I study all day.
אני מנסה להוריד את זה שני
You
שמש.
closed it was just happening at the same time. No, it's good.
Do you have a class next Monday?
Next Thursday is no class because instead of next Thursday, we go on Sunday to the MEG lab.
Okay.
Because we couldn't do it on.
So can I present it in 2 weeks?
Yeah, let's see. So the problem is that it was shy, but I took him out. It was good. Then let's just start this. Okay. So last week we went to the EG lab of Philamid, and the data will be available on Moodle or time. On Sunday we will go to the MEG lab. One of my Chinese friends. Last time we missed it.
Yeah,
Because
for
both of you, right?
I don't know where is where is it?
You don't know where's Gonda?
Yeah.
Okay. Gonda is in the upper end of the campus. You have to go. Let's explain Gonda. Gate 5. Yeah. Gate 5. So basically you go in the direction of the rice house. Okay, and close you come to the rice house. Just do the run where it's nicer and follow this direction. Then you arrive at Gonda. So we can go together on Sunday. Okay, we can meet and go together. Let's meet Sunday at 11:45 in front of or at his office. Okay, 11:45 at his office. You don't have classes, right, on Sunday?
Yeah.
What? Yeah, you have.
I
or-
don't have.
You don't have. Good. So 11:45 in his office, and then we go together on Sunday. Good. Scheine will be there. Can you open the door again for us, or otherwise you will go out? But if you can do it, this would be nice. Good. So what I agreed with Ari is the professor of the head of the engineer in London. So I discussed with him and to start finish my part and try, and then you good. Also for the condition, right? There are two conditions. Remember the one that was driven by the beat, and the other one is freestyle. For the bandpass filtering, you can use Yarden and Bonin's script that we discussed last week. It's already on Moodle, or I think Yehuda also have some filtering, right? They work in a different way. Matter. And once we have then extracted, you then of course you need to perform surrogates, because you don't know, sometimes this coupling, this synchronization can happen by channel. Okay, so you want to know what is the background level, so to say, of serious synchronization. There should be no coupling. Combinations, and you get a kind of a background noise level, so to say. And then you see how much your reader synchronization is above this level. Okay, if it's above this level, you say it's a significant coupling, and you basically have a link in your EEG network. Okay, you have an EEG network of 8 nodes, and you would have a link in these 2 nodes, and then you can take the split nodes there on network. And then you will have, for let's say freestyle, you have 2 students in the room. Then for each student you have 1 network. Okay? For freestyle. Then you have another This is the next one.
Oh.
This is the next point. So this is the is whether there is a coupling between people. Okay? We can not go so much into details as they do, but we do a very simple analysis. We take again alpha band, but now we overview this with metal. So we take for each alpha. value of surface, and you have to show that it is significantly different than anything you get from surrogate tests.
What is the functionality of alphas?
Yeah. Just signals from all, okay? From the front to the left and one right.
2 from the X.
2 from the 8. I mean, you have to do all of them, right? You have basically a matrix. This is the adjacency matrix we talked about in the network lecture. And then you do a real adjacency matrix. That means you take the signals as they are, the alpha signals, and you calculate the signal rate. And then the surrogate matrix will be where you take the real signal and the other one will time inverse. You basically synchronize the beginning of this one with the end of the other. And this should not, still there will be synchronization because it's just happening by chance, but not as much as you, or maybe yes. What is the, if you get the same level of synchronization for the real than for the inverse, what would be your conclusion? There's no synchronization, okay? So if it doesn't matter whether you time inverse the one compared to the other, then there is really no cut.
So just check yourself to say something about
Yes, yes. And good. And you should do I think right, so maybe you do a distribution of this real time inverse. Okay, so you do it for all the combinations and you get a distribution. Okay, so you have 8 times 7 combinations, right? And you always time inverse 1, so you will get a distribution of 8 times 7, 56 values. Okay, and this will be find the mean and the standard deviation from this. Standard deviation or standard error, what is the standard error? Standard deviation. So now you have the mean and the standard deviation, and now you start calculating the real thing, right? So you take the first two pointed and calculate the synchronization, and now you get the value and you compare it to the mean and standard deviation of the surrogate. If your value is much higher than the the standard deviation, it's fine, you take it. You say it's significant. If it's within mean plus minus standard deviation, you say it's not significant. Maybe you do it like this. Everybody agrees on this? I don't know how to do this out. It's no idea. So it's work in progress.
Let's start with both campus will cover the same only the chip. So if you're trying to compare one to the other, it will not be that random because that's the couple of the system will face you. So I don't think the background will that's not your PFP value is above 0.4.
You mean now for the second
Yeah,
time
exactly.
survey?
One
It's a good point. It's justified, right? This argument. And I think then you should just only take the surrogates from the same condition. So you take
only for the freestyle.
when you want to calculate the freestyle.
This is easy, but for the first part when we are both of us coupled to
Yes.
the noise, to the
Yes.
beat. So what can we do over there?
So you're
So we can just reverse the time?
no surrogate. You also. I mean, for the second when you want to
Yeah,
study
me and my
coupling,
yeah, exactly.
then we still take you and Leon.
Although
Yeah,
we're
the
still
beat.
coupled to the same beat.
Yes, because this would.
It's the same beat, the same duration,
Yeah,
same.
yeah. So if there is no difference between you and Metal
Mhm.
and you and Leon, then there's no coupling.
Okay,
Yeah,
it's
if it's
coupled.
the same,
just
that
to
the
coupling
empowerment,
is with
not
respect
the interaction between you.
You are absolutely conditions.
So I mean, we are now exploring. I don't. Maybe we encounter other problems along the way. I don't know, but it's a little bit. I'm excited to see what comes out. And I don't have a good feeling about it because I never did such studies. Shai probably has a feeling. What would you? No, maybe you don't say. No, maybe we keep it for when we discuss the results. Good. Any questions on this? So you really, if you, if something is not clear, you have questions, you cannot work with the script because there is Then let's talk a little bit about MEG. So, I mean, there's a lot to talk about, and I don't know so much about it. I will just tell you with some presentation I found on MIT, at the MIT website. So, and I thought it's enough for us. And I just tell you the stuff that you need to know for the course in order to do the projects, okay? And that you're a little bit prepared when you're going to the class, to the lab. So MEG is magnetoencephalography, in contrast to EEG, which was electroencephalography. And basically, instead of recording the electrical activity of the neurons, instead of measuring the electrical activity of the neurons, you measure the magnetic fields that result from the electrical activity of the neurons. And the magnetic fields of the neurons are very, very small, even when you sum up over clusters of neurons. So we need sophisticated technology. The most common is to use these superconducting detectors and amplifiers. Squids. We have here a research group that works on squids. Dina is doing this, right? She's an expert on squids. And using squids in MEG to detect the tiny magnetic fields is the state of the art. However, hardly superconductivity, right? You need helium to cool them, and helium is quite expensive, and helium has a high rate of, I mean, it evaporates a lot, and you need to refill, and it's quite expensive. So he changed to a different system. He built it. I mean, there's a company that has developed a different system, and they sent him all the parts. Last year, nobody of the engineers from the US wanted to come visa. They were scared. So they sent him everything, and he built it himself. So maybe you can tell us a couple of words about this, how it works also. So the magnetic fields are analyzed, and usually what you're interested in the hospital and in clinics is to find locations, to detect locations and neuronal sources within the brain. Why? Because when people have epileptic seizures, they usually have a source. Not all epileptic seizures, but a lot of epileptic seizures have a source, you know, and then you can help this person by doing a surgery and taking out the tissue there. But there are also seizures that are all over the brain. Then it's very difficult to operate. So, so they do this a lot. You can also do this with EEG, this source localization. This is amazing. For example, they implant the electrodes into the brain of or the surface of the brain of the children with seizures as a result, and this magnetic field passes through the skull. Okay, so there's no damping involved. So you have somewhere here a neuron that is active. So you measure just on the surface the magnetic field with some detector that here involves squid and is cooled by liquid helium. And so, and as I said, it's very, very small and needs this sophisticated sensors. And then you do some source localization. You take some model, some dipole model. I don't know how to do it. Okay, and you can pinpoint it on this MRI picture to exactly know where some seizure happens, you know, in epileptic seizure, for example. So these are examples. You can't see it probably; it's too small, but you get a picture like this. These are all little spike waveforms, you know, all over the. I mean, these are here how many? 148 MEG time series waves, and here, for example, you have this characteristic spike that is typical for an epileptic seizure, and then you can do some field map. I just tell you that it's possible. I don't know myself how it works. Okay, and from here you conclude it is in the left temporal lobe. Okay. So why is this left? Because the patient in the MRI is laying like this. Okay, so you're sitting in front of the monitor, but the patient is basically laying like this, so the left is here. Okay, so that's why left is here. It's also always written. Okay, so you have, yeah, there's not much to say because I just don't know. I just tell you it's possible and we don't need really to work with it. What is more interesting is this plot that shows you here the spatial resolution versus the temporal resolution. Okay, and EEG has a very good temporal resolution, but sucks when it comes to spatial resolution. Okay, it's about 2 centimeters only because you always get cluster information from the EEG. However, the MEG has both, has a high temporal resolution comparable to the EEG, and also high temporal resolution, but a much better spatial resolution. Okay, which we don't use because we don't do any localization. And this is comparable to what I told you about Boston Children's Hospital, where they have this IEEG, which is the invasive EEG, right? Invasive EEG, getting closer to the neuronal source, has also a much better spatial resolution, but it's invasive. Okay, so you have to have surgery and put it in. You have here as comparison fMRI, which is, I mean, okay, spatial resolution by now, but the temporal resolution will never be as good as the MEG, right? Because you have to switch gradients, and for anybody who knows how MRI works, you have to switch gradients, and you cannot do this super fast, okay, to locate. To give you, I can also give you a talk about MRI, but not today. Just to explain why you never reach some temporal resolution with MRI that is comparable to MEG. It's impossible. And then you have PET here. This is positron positron. How's it called? Positron emission topography. It's when you you have to inject a radioactive marker that emits positrons when they're on the brain, and then you just measure basically a metabolic picture of the brain. So here the MEG measures a really functional picture. Okay, it's not metabolic. That's also fMRI doesn't measure it doesn't give you a real functional picture, it gives you a metabolic picture, because it highlights the places where energy is used, you know, and oxygen is used. So it's not really giving you the picture of the neuronal activity, so to say. Yes. Any questions?
What do you mean by metabolic picture?
Metabolic, so here you measure really the neuron. With EEG and MEG, you measure really the neuronal activity. With the MRI or fMRI, you measure at which place oxygen is used, so to say, or glucose is used. You know, so it's not directly the activity of the neuron; it's more a cluster of neurons that needs glucose to function, basically. So it's not 100% the neuron itself.
Yeah, maybe it's not also related to the electric activity.
Maybe not, yeah. It can also be just, but in the brain, no, you also have other tissue that uses up. So,
yes, we have Lia cells.
Clear cells and all these other astrocytes.
Yeah, it's type of Lia cells.
It's also clear.
Yeah.
They don't really help.
Supportive cells. They are
feeding the neurons, they support the structures of the neurons.
They don't help you in thinking, they just help you in building the structure, so to say.
It's also active as opposed to MEG, which is passive, because MRI gives you a pulse of magnetic field and then you see the alignment, right? MEG just, it's passive, just detects all the time.
Yes.
So MRI, if you have a seizure and then you do a pulse of MRI, it will act different
Yes.
than MEG.
Right. And you can also not really, the MRI would not be able to
Distinguish.
give you a picture of the seizure because it just takes too long. And the picture you see in the MRI, so these pictures here, they are averaged over many measurements. Okay, you have to repeat many measurements in order to build such a picture. You have to do 5 minutes measurement, okay, to get such a picture.
Of active seizure or just passive brain functionality?
No, this is just anatomy. Okay, I'm not talking about this. I'm just talking
And when
about
you talk about this,
the fMRI.
no, about MEG. If you see the seizure, does it have to be? Does the patient have to have a seizure right now, or is it a position in
Yes.
the brain where there is?
No, it has to be at the same time. But
Has to be at the
one measurement is enough.
Okay.
Okay, it has to happen during the measurement. And how they do it in the experiment is they can provoke seizures, right? Epileptic seizures they can provoke. There is an easy paradigm. You probably have heard about these.
Pokemon episodes. A lot of flashes.
Yes. In Japan, there were
Yeah.
in the 90s, I think, some. Was it Pokemon?
Yeah, total blackout of entire
Yes,
seizures.
and many
because of-
children
Yeah,
got blacked out by because this flashing made them epileptic seizures. Yeah, it's crazy.
Also, preventing sleep.
Can prevent sleep and also can make
mean,
you
in-
better sleep. It depends what frequency you use. Yes.
No, but when you want to induce epileptic seizure, you prevent someone from sleeping, and then they.
Yes. Yeah. But you can also, there was once a lecture paper, I think 15 years ago, by a German group that showed that with magnetic stimulation of the brain, you could induce deep sleep. So they had so they just made a magnetic stimulation of the brain in the delta frequency wave that we discussed last week. Okay, this very low frequency of 1 second or 2 second oscillations, and they put this stimulated like this the brain, and they caused people to sleep or fall into deep sleep or something. I have to look it up, but it was very interesting how you can do also and not only measure brain signals during sleep, but you can also influence sleep by this. Yes. Main drawback of MEG is that it's very susceptible to noise. Okay. If you look here on the y-axis, you have the magnetic field. Okay, in logarithmic units. So here is from 10 Tesla to 1 femtotesla. Okay. And you see that MRI has around 2, 3, 7 Tesla, and the magnetic field of Earth is 1 Gauss, right? 10 to the power minus 4 Tesla. And noise that is just around us is many orders of magnitude above the noise, above the signal that you get from the MEG. So you need to shield very well your room, okay, that this is not affecting you. So you can ask him, for example, if when the light rail, the racket with Kala will pass the university, if this will affect his measurements.
It's also the same for squids. Bina has the same challenges like now.
Ah, yeah, okay. So what is she doing?
They have a room at Nano.
They need the shield room, right?
They have a sheet floated room, by the way, floating room as well, because
Of the vibration.
yeah, exactly. So they have it at -2 at the Nano Institute
So,
in talks. The problem is only trucks in the middle of the night. On gear. So everything
on
is-
gear.
Yeah, on gear.
Wow.
It's that sensitive.
This reminds me that in CERN, in the 90s, I think the end of the 90s, when they run experiments in the CERN, they got always very bad measurements in periodic times. And they didn't know why, you know, always big deviations and errors and measurement errors, until someone matched this with the TGV arrivals in Strasbourg, I think. so it's crazy, no? How, I mean, over such a long distance, you have a big effect. Okay, so I don't know. Actually, I mean many things to ask him. The heart, the QRS complex of the heart is also causing a magnetic field, which is 2 orders of magnitude above the strength of the MEG signal. So how is he shielding this? Any idea? I don't know. Because this you have all the time, and we see it also in the EEG sometimes, the ECG. But how you, maybe you just also record the ECG and then you deduct it from the signal?
I don't think he recorded it.
He's not recording it, no?
I don't think so.
So I don't know. You see,
Can't you just subtract it somehow?
when you record it, yes, then you can subtract. Because you don't really know. Okay, you say it because it's periodic, maybe. I don't know. Okay, just something to ask him and maybe to pay attention when we do the analysis. Good. Yes, that's basically it.
Well, I heard at first that the plan was that the rail will go under Valleyland, but then due to the sensitive measurement in the nano building, so now they turn.
Really?
This is why it's in the front.
Yeah.
Only because of Bina?
It was to go underneath
Underneath
yeah,
the yeah.
throughout the entire university.
Underneath the nano building, and I heard that due to
The
their
university opposed to that,
Yep.
and then they changed that.
So because of Bina, we have to pay now more tax.
Bina it up, but yes.
Actually, not taxes. Arnona you pay. I'm in Tel Aviv, so I think I don't pay for the Arnona here. Is it
It's part of.
Is it paid from the government or is it paid from the area?
Who pays the government?
It's the area or is the
ארנונה זה עירייה.
no, Arnona is area.
No,
Yes,
yeah.
but the light rail is Bishvat
private
HaTorah.
I guess.
It's a private
But
company.
who pays for that?
The government.
No, it's still a private company. They work with the government,
But they get
but it's
probably
a
a lot
private.
of.
I work there, so
You work there?
yeah.
So you get, but you also get money from the government.
I'm
as
not
investment,
in
no?
that company, but I work in the security part of the
Ah,
light race, so
okay.
I know it's a private company.
Okay.
They got
But they probably
I
get
don't know what to say.
taxpayer
class.
money.
Yeah.
Yeah.
Didn't class.
Yeah.
I don't know.
So they get taxpayer money, I think, to make that.
I think they pay the taxable.
Oh yeah.
I don't know.
Later they have to pay tax when they.
Yes, but it's
run
not
the-
our taxes. It's the company.
I mean,
It's a
you're working
private
for
company. It's not
Yeah.
a government
them. You're
company.
working for them, so you're biased. I don't believe you. Yeah, of course, but I think they get some.
Good job, no taxes.
Some substitution.
It's a lot of companies
Yeah.
together working underneath the government.
Okay, I see.
It's private companies.
Yeah. When are they going to finish actually? You know, this?
They just prolong it for another
Yeah.
3 years, I think.
Ah, okay.
The parallel line will be in 27 maybe, or and the green one will be 29.
Okay, good, but it's not
Last time.
too far down the road. I took now the train from Tel Aviv to Petah Tikva, and it was so nice. You know, you don't need to stand in Jabotinsky traffic jam in the morning. It was in 5 minutes we were in Petah Tikva. It was amazing. 10 minutes, I think, instead of 1 hour. Good. So yeah.
It's not that good.
Okay, so
I know the problems there.
Okay, you know better. I was exaggerating. So, just for you to know, for surgical planning, MEG measures directly brain functions, as you said. High precision, millimeter resolution. So you want to get, if somebody needs to do a brain surgery, you want to get an MEG, right? Because it has really pinpoints really to the millimeter. High temporal resolution, milliseconds, and you can adapt it to many functions, right? If somebody needs to check some motor functions, right? You can do this by finger tapping. Then you activate the motor cortex, and you can see this in the MEG. Non-invasive, easy to use, and that's it. What I know about MEG, and I think enough for us to do the experiments on Sunday.
But it have a problem because it measures only neurons that align parallel to the skull.
Ah, yes.
Because the magnetic field is going out.
Right, yeah. But I mean, his helmet also measures occipital, so it goes around.
Yeah,
right?
I do know, but they have a problem with neurons in different orientations.
Yes. Yeah, so it's not easy. You really have to spend your whole life in order to become an expert in this. But we only touch the surface, so to say. We only get some data, and we try to do some analysis for you to get comfortable with data analysis. If you later want to do your PhD in this field, then you learn more, right? Necessarily. Good. Any questions? What we are going to do with the data, I don't know yet. I need to ask him what is interesting to study, given these 3 different kinds of pictures. So, good. Then let's switch to Shai, talking about the data structure. You can do it on my computer, or?
Yeah.
Yeah. I downloaded them, but I don't have MATLAB. So how did you?
So just I'll explain and talk about it, but we don't need to show it.
Or you
Maybe
want
the
to
names suggest.
the names. Okay.
No.
So let's do the names. Good. Yeah.
Okay. So these are the files. Currently they are math, but you convert them. I named them based on the condition. We have beat and freestyle, FS for freestyle. For each dyad, each pair of participants, each pair is numbered by 1 is the first pair of participants, and 2 is the second. And L is for the left participant who sat next to the door, and R for the participant who sat next to the window. The data structure is pretty simple. We have 8 columns, each column for each electrode. I now reckon.
What was the time?
The time is in the row. We don't have. I don't enter. Actually, it's 500 hertz. So I reduce it to 100 hertz. So it's each row is 1 divided by 100 of a second. So now
did you write the channel on each?
That's it. I didn't
each
write.
column? Ah,
So maybe I will upload the names of the channels for each.
but it's in each of the files the same, right?
Sure. Yeah.
So then we just put the README file, README EEG on the Moodle, and there you write the 100 Hertz. Okay, that is 100 Hertz, that you know the time resolution. And we write what column is what channel. Right?
And
That's it.
and that's it.
Good. Any questions about? So you do this, or you will do the conversion, and maybe next week. When do you have time? I cannot say.
It will be ready at the next week.
Next week, okay. I will update you on Moodle that it's now uploaded with all the readmes and stuff. Okay, very good. Then we have the first set of data. Any questions?
What is the values?
The values.
The values.
Yeah, it's the electrical charge between each electrode.
Actually, voltage, no?
Voltage, right?
Yeah.
Yeah, voltage between each electrode and the mass to it.
Ah, you already do the derivative. Okay.
Do you know the units?
It's micro.
It's micro.
It's microwatt.
Microwatt. Yeah.
What's the sampling frequency?
100 hertz.
Yeah.
Originally it's 500. I reduce it to you
Yeah,
have
that's good.
small files. Not
Yeah, we don't need so much.
Yeah.
The baseline is another channel, or is it already subtracted?
It's obstructed.
The baseline, you mean to the master?
Yeah.
Yeah.
He did. He just normalized it by the M1 and M2. Okay, good. So then everybody knows about the data. Good. Then Yoda and Ori want to talk about the scripts. You need to upload first the EG, right?
You can just drag it.
Okay, good.
So it's
No, we don't need to run that.
Gil, can you actually see this from there?
Not very much.
Okay. Otherwise, I would have liked to give me the telephone number of your eye doctor. I have a very good vision. I don't see it from there.
in Python that it's easy to work with the Panda when you get files. So we using Panda, create a file, and then we divide it into time, the data itself, and the names. And afterwards, we have
Oh, very good.
yeah.
And you also did a good job in writing everywhere.
We were very bored. So.
No, it makes it very easy for the students to take this and modify it.
Yeah, so all the channel names, which are the electrodes here on the plane, each one will or something. So it's arranged in a column like that, so we have a column of time, and we can, from the time we can calculate the frequency.
Which first given this was for the data files.
all the names of the channels, this is the background details, and you can see the sampling all that is 125.
For example, we take the FP1, so all of the electrons, and let's show it as a function. Okay, so the volume the sensor is measuring, and with no filtering, no meaning, just present first with the time, and so the FP1
This is a Parkinson patient that is walking along a corridor. Okay, so like this, formally, then he's coming back, then he turns. This is his turn, okay, and then he walks a little bit faster. There's the next one, and then you see a little bit increase in everybody can have drums. I was just excited, sorry.
Okay, so the next thing is to do filtering. Any range of frequencies.
And now
Again, the two
here we cannot see anything that is different from the first one. You can see first of all that the amplitude is much smaller because it was minus 100 to 100, so the standard has in the
Okay, so now we want to talk about the phase relationship between channels. Okay, so for each measurement we have the amplitude of the measurement and also the phase of the measurement. Using the M&E library we can extract the amplitude and the phase.
the Hilberts.
Yeah, using the Hilbert transformation, we can extract the amplitude and phase. Right, the Hilbert is not inside the.
Yeah, exactly.
And then we present.
So somebody remembers what this analytic signal is doing? Not you. Yes. We talked about it 2 weeks ago. Analytic signal function, what's it doing? Transforms the measure signal into a complex signal. How are you doing it? Takes the measure signal as the real part and the Fourier transform as the imaginary part. Not Fourier, the Hilbert transform as the imaginary part. And what is the Hilbert transform doing? Not mathematically, but just how to say it? Just
Reenact it, maybe?
What's the purpose of doing the Hilbert transform, so to say? What does it do? Crude language. It shifts a signal by pi over 2. Okay? So a cosine becomes a sine signal, so to say. Okay? Good.
But the most important part is that now the angle after this transform is in fact the phase, which is easier for us to handle. So if we just take the angles after doing the Hilbert transform and plot them, here we've plotted for a given time. We just taken some indices and plotted them. This is for the first sensor. You can see the phase. By the way, what we've done is we locked it between minus pi and pi for easy visualization. And this is why it's so nice. We can see here the slope is because it's sines, but we have here some, small transition. Exactly. So this is for the first channel, and this is for the second one. Can we zoom out a little bit?
Oh, sorry. What is this little bump?
This little bump because they are all coupled, so they're all manipulating one another. There's small shifts in the brain. There are stuff that are happening. It's not just a sign that keeps going on and on and on. This is how the brain functions. Then we can see that although there is also a small shift in the other one, but it looks different. It's not the same phase. But here in this case, we can see how the phase goes according to time.
Yeah, and now we subtract. We've seen them separately, the two channels, and now we subtract one channel from another and present the result as a function of time.
Here we have some nice stuff. Here we can see this is the phase difference between these two detectors as a function of time. You can see that they go all over the place. But if we are taking that and put it inside an histogram, we can see that most of the samples are around 0. 1 second. Are around 0. That means most of the time they have the same phase. And also, you know, they are going to be -5 pi.
And this is now, which channels did you take?
Just the first and second.
Next to each other.
Yeah,
Okay.
exactly.
So
We can do it for all of them. We just chose randomly
Yes.
0, 1.
So when you, I mean, since they are next to each other, you would expect, I mean, the communication between is in milliseconds, right? I mean, it's very small distance between, so you would not see any offset, so to say. But if you take, for example, channels that are farther away, then this may change also, right?
But if you want, we can just take another channel after we finish that and just
Okay.
run it and see the
Okay,
different
and see if
results.
there's also.
Yeah, it's very easy to handle this code.
Yeah, yeah.
And lastly, what we wanted to do is to see the accumulative phase as a function of time and also the phase difference between them. So this is the two channels, this is the accumulative phase. To do that, we just, there is in NumPy the function unwrap. There is this little thing. And this one, unwrap. As I said before, this is between -pi and pi, but if we want to accumulate that, we just need to sum up the entire time and not to make it inside this
Kind of cancelling the boundary,
The boundary
conditions
conditions,
and
exactly.
build it one over the.
Yes.
So, and again, if we just subtract from one another, we can see that is almost 0 with small fluctuations for these two specific channels. Okay. Now, if it's okay for me to go on?
Go.
Okay.
After you haven't talked at all.
Now
so
me?
far.
Me talking? Yeah. So now we are talking about the phase locking values, the PLVs. And in this section, what we wanted to see is the mean of the phase difference, the absolute mean of the phase difference, to see if they are coupled and when they are coupled. So first of all, what we wanted to do is to calculate the phase locking values, same as later. Everyone got there. We just want to know if we have two different modes, if they are coupled to one another. Again, we are using the same function. This is the function that we keep calling it. Transform, then calculate the angle, then the phase difference transform, and then we just calculate the absolute value of the mean of the phase inside the exponent. That's it. Very, very easy. And we will do that. What we want to do is to do it for the entire system for all the detectors. Calculate the entire results, do the mean value, the phase value, and just plot it inside the matrix. Because in matrix you can see how two different channels react to one another, and it's not supposed to be diagonally synchronized. And because there's no difference if they go to this one, to this one, to this one. So when we plot that, we are supposed to do one with 0 and 1 because it's the amplitude of the following phase and it's the absolute value. You see some exciting things. The first of all is the diagonal. You can see that it's purely 1. And why is that? Because
One is fully synchronized.
because
The one with itself.
exactly it all the time synchronized with itself. It's the same vector, so they have the same phase. So okay, this is nice sanity check to see that it works. We know the diagonal part is 1. Then we see some heat map between 0 and 1s, and we have this little arrow, and this one is just zeros. Maybe the patient is there in that one? No? Or maybe this is an artifact. So
Can you go
to see how that patient looks like. Yeah, of course.
and then type Titan Asher, EEG architect.
patient is that in this?
That is a different patient. No, this day this camera did go. I don't know why. Okay.
So this is what we want.
Yeah, just you mean the B?
You have to. It is matrix, right?
Yes.
But it's a block matrix. To check three things, although just one of them. We wanted to check if we have an entire row of zeros, entire rows of 0 to mean none, entire rows of infinity values, or just a constant. It's something that is near constant. So it's easy to check for none or infinite, so just if, I will not write that. And for constant, there is a nice function which is called exactly, and what is this one?
all close.
All close. Exactly. So this one we've checked. It's if there is no, if there is a fluctuation smaller than 10 minus of 8, then it means that it's a constant. So for us it was very good. And when we run the script, we see that we have the value that is non-infinite values, and the channel as that is channel surprise to find it's the same channel. So we just reshaped the data itself, we deleted this channel and reloaded that again. This is the clean data without that. Nice. Now we can work with that. And this is great. Again, we've got the nice diagonal parts, we've got parts that have less synchronization, and ones that have more for the entire time series. The entire time series is nice, but is not what we intended to search for. So we wanted to do it the PLV as a function of time.
So here the blocks that you see it is the hemispheres. Right? The upper block is the left hemisphere, and the is the right hemisphere, and this blue stuff is between the hemispheres. Less synchronization, not communication.
So now we encounter a new problem. How can we take the PLV and measure it as a function of time? The PLV is the mean value of many samples, and we want to know how many samples we can measure in this section. So I started to say, okay, we know that we measure alpha waves, right? We know the frequencies of alpha waves, 8 and 13 Hz. If we take sufficient repetition times of alpha waves, which we call the window time, we can say that, okay, now we can measure this part and say, was this part synchronized or not? So we started with around 5 repetition times. After showing around 11 results, it told me we can raise it up, so we took 10 repetition times. And then we wanted to know to slide the window to get a nice continuum function. So the sliding part, the shift, is half the size of the window itself. And when we do that and we calculate the PLV over and over and over and over again for the entire spectrum, we can see this nice graph. This graph is for the entire system. It's not a matrix, it's for the entire system, the mean value of phase lock for given times. We can see the time sometimes it's very, very high, sometimes very, very low. This is nice, but again, some nice lecturer told me it's not enough. Take that and make it nicer. So there are two ways to make it nicer. The first one is by just using the smooth function. The smooth function keeps the same time, but manipulates the data itself. Because now we don't have the exact point. We have something between points because it does a call depending on which type of method you choose. It takes something in between the values. And we've done that. We've taken sigma of 0.8 equals to 3. We can change that on broader or narrower windows. This is the first way to see the data. And the second type of making the data nicer is not by smoothing, it's by revealing it. That means that we will have lower resolution because now we will take just adjusted values and just reveal them into a single value. So we will lose the time resolution, but we will keep the same values over and over again. And we've done the same course again with bin size number 3. That means that now we have third times of bins in the system. And this is how we look at it like that. And to be honest, I don't know. I really like the original data. It's up to you what to choose. Anyway, so
the clean one was sufficient. The clean smoothing was.
It looks good, of course. It depends on what you're searching for.
I think what I find interesting is the entering into synchronization and in and out of synchronization. I need to study it between participants, but it's nice to see it in one people.
Yeah, actually it's nice because again we have functionality to work. So this is just exactly what you said to the last part of this entire data analysis. Let's figure out when was the highest synchronization and the lowest synchronization for the entire process, which is super easy. We can just search for the max and the minimum of this function.
Which you can see on the plot.
Yeah, but don't destroy that yet. Okay, so when we do the code and rerun the entire thing with the matrix, you can see that we have the highest synchronization part is following 80 seconds and the lowest synchronization part is after 101 seconds. What you said, after 100 seconds, the patient turned around and he lost it. We can see that according to this mapping. After 80 seconds, it was in the middle of the first and the second. The first one was around 50 seconds. The second one, 100 seconds. It was in the middle of that, and it was in the, on the way back. It was fully conscious, and his brain was in the highest phase lock. Yeah. So this is for the highest phase lock, and this is how the matrix looks like. You can see that it's a lot of red. And if we are looking on the least PLV time, you can see that it's out. Yeah, it's out a little bit.
Nice. Yeah.
So I think this is enough for now.
No, this was pretty good. Yes.
Only I can do it.
Yeah, the paper is already published.
I will cite that one, don't worry.
Good. No, it's nice, very nice. Thank you. So this is now, I mean, was very comprehensive. You don't need to do all this for task, right? It's clear. So you pick the stuff that you need in order to do the task, and we will not do the windowing, or maybe we will. I don't know. To do some windowing, yeah. But then, if we
Confidence,
calculate networks for each window. It's too much.
No.
So maybe you show also the synchronization over time, like Ori and Buddha did. This, but the network, you can just calculate over the whole information. Right? You do basically an average. You take the clean curve that you have there and you average it. And this is your synchronization value. I think I will change this in the instructions. Yes.
Why do we? What is synchronization defined by the phase locking? How is correlation between the nodes?
So correlation is a different measure.
It does not measure synchronization.
No, correlation measures the amplitudes. Remember, we had this when we talked about the chaotic oscillators. We showed maybe I can just take it from the last time. Yes. So you see this? These were this experiment of standing still, and then you have to sway to the front and to the left and right, and these are the data. Red is forth and backwards, and black is to the side. And we wanted to know whether it's there's a coupling, right? And then you can just look at the amplitudes. You just take here the amplitudes, the instantaneous amplitudes, and you plot them. The one amplitude for the red versus the other amplitude for the black, right? And you see, I mean, okay, you can argue maybe there's some correlation here, but
Is why the amplitude corresponds to correlation?
Let's say here. Okay, so here you have really chaotic oscillators, and nobody would argue that there's no correlation. Okay, but no, this is the amplitude derived from the signal. And if you would have, and then you plot the one against the other, and you get this straight line, then they are correlated. Okay. There's no question about this.
Is
You
it
can
the
also
definition of correlation according to this? Okay, this is the
correlation means I mean either it goes like this, then it's positively correlated, or like this, it's negatively correlated. It means I increase in one system increases its value by whatever in the positive direction, the other one also, or vice versa. You know? Then it's positively correlated. If the one increases in one direction, the other one at the same and the other direction, negatively correlated. So you would see this in this plot. And you sometimes you have systems that have correlation and synchronization, and sometimes you have just correlation and synchronization, or sometimes you have no correlation and synchronization, like here. Okay, it's a different measure. Look at the amplitudes. What Ori and Yuda did was they looked at the phases, at the frequency oscillations, right? And then, I mean, for this case, you get very clear synchronization, right? So not so much coming from here. Maybe you can say there's a weak correlation. I won't argue about this, but the phase difference is very stable. So this is really synchronized. Okay. Good, but we don't look at the amplitudes in the EG. It's too much. Let's do just. Okay. Good. Yes, other questions?
So no networking for the region?
No, we
Because
we
we
are
need
not the amplitude.
amplitudes for the correlation for the
No, right?
just for okay, my bad.
Your matrix is just the value. You only take a phase difference, right? You don't take an index. Okay. So, but it's fair enough. Okay? I think. I mean, if we don't get results, we have to change a little bit. So, but we will work with what you did and see how it what we'll get. Yes. Any other things, comments? Good. Then we are this actually everything that I wanted to talk about today. So on Sunday we will meet at maybe 5 minutes to 12 or 12 o'clock at the again. And we are for if somebody comes late, it's on the 4th floor, the MEG lab.
When?
Sunday. It's coming Sunday, 15th. Because we didn't have time next Thursday, so we meet instead of Thursday, we meet on Sunday. We don't meet next Thursday, okay? And we also don't meet the Thursday after because it's Hanukkah. Then we meet again in 3 weeks after this. Okay? Good. Thank you guys. Have a good Shabbat and see you on Sunday. Yes. If you have any questions afterwards, just write an email and we will.
So on Sunday, I have a class until 1:30, so I'm going to come later.
Yes.
Is that possible? I mean, I can try to do something on Sunday. I'm not sure I'll make it.
No, it's too short of time. I think what if you are not getting to start yet with your project, maybe you can start not synchronization, but autocorrelation. Yes, this is
Of each channel itself.
אחרת אתה הוא יושב ככה.
כן.
Yeah, thank you. Shabbat shalom. And then we calculate the autocorrelation situation for any information in these kind of signals. And we certainly want to use the DNA in order to implement some data analysis. And there are packages on online that you can use to properly filter the data and then calculate this UFA. And you get a spectrum like this of UFA spectrums. And if it is above, if it is around 0.5, it means there's no autocorrelation, it's random. If it's above, it will be positively correlated.
DFA
Is the name of the analysis.
Okay, so in that, should I work on the MEG data or the EG? Or
Maybe,
it's pretty similar, so
it's pretty similar, but I don't have to know. I don't know anything about MEG. EG, I know that you are supposed to get autocorrelation.
okay.
Positive correlation. So I can also do this. And then we ask the students to use your code in order to calculate
The
DFA stuff. Yeah. If you want to do this, you have to solve it yet. If you want to do this, write you an outline again,
Okay.
and then we can use this.
Yeah. So
with the driven, this is in the autocorrect.
okay. Build the skeleton, the script for the autocorrelation of DFA analysis.
Yes. The EEG data to train with, the same that they used.
Uh-huh.
It's good to train with, it's short, it's easily to handle. And then you just use this data and do the feedback.
Okay.
Good. Okay.
And when should I present it?
After Hanukkah. After
Okay.
Hanukkah, when we talk about these EEG analysis that I present, I mean that I ask everybody today to do. We will talk about this after Hanukkah, and then we can also look at autocorrelations.
Okay. And should I reference in the presentation to the fractals and
Yeah.
Yeah.
Say that this is from lecture 3. We discussed there what DFA is doing. Maybe you can repeat a little bit that everybody will remember how DFA is working, and then you take the data and you copy it.
Okay. Okay.
Good?
Good. Maybe I'll like ask questions if I have stuff.
Always. Shoot me a question if something is not clear. Now write me a question, write me an email with the question or with just the request to send you detailed the steps
Okay.
that you should present.
Ah, okay. The instructions for the
The
presentation.
instructions for the presentation. Yeah.
Okay. Okay.
Good.
Thank you.
That I don't forget. Okay.
Yeah.
Yes.
Yes, I have two questions.
Yes.
One is the course notebook. Do I have to use Jupyter or I can just use whatever?
For what? For the course book.
Because, yes, for the course notebook.
No, Jupyter is better. When I check it later, I load it into Colab, and then I look at what you wrote and I run your scripts. PowerPoint, I can run the scripts. You know? So, but why you don't want to do it in?
Because in Word, so I have other questions. Yeah, I'll try.
Yes.
It's not problem. Second
Yes.
question
Yes.
is I have the tasks on human gait analysis.
Mm-hmm.
When will I get the instructions?
Write me also an email, and I will send you back the instructions. I need to think about it, and I was just thinking now until Hanukkah, and after this I will think about the next step. But write me an email, and I reply to you with the instructions.
Yeah,
What to
sure.
do. Okay?
Okay.
Good. Good.
Thank you.
Bye. Bye.
Bye.
Bye. Shabbat shalom. So, Josef, what is going on with this?
Yeah, so I'm trying to processing our data.
Yes.
So the last fields I can process it from 150 to about 400 is it can process not code, but just can process. But the remaining 100
Yeah.
they can be processed. So I want to record in the data set if it can suit the program.
Uh-huh.
Yeah.
So you can read and look at them, but you cannot what means process to